G'day there, you're watching the Aussie BIM Guru. Today I've got a really quick video where I'm talking about excavating site and measuring the excavation using Dynamo. So there's a few ways to do this, but I'm going to show you how to do it in Dynamo. So I'd like to thank Ruben from Copenhagen for coming to me with this question. It is a good question, and whilst there are some methods such as using, I think they're called graded surfaces, graded regions, I have found that people do find this method quite confusing. And I've also received inconsistent results from the inbuilt graded region workflow before in Revit. Whereas this workflow I use is actually quite accurate. It just uses the geometry of the excavation and the site to find the accurate volume of cut into the site. So I'll be using two custom nodes in this workflow. One of them is actually from my own custom package, which you can find on the Aussie BIM Guru GitHub. It's called Crumple. In this case, I do have a video on my channel that talks about how you can install this package. In this case, it's called Surface Clamp Z. And essentially it just gives you all the surfaces in a piece of geometry that face within a tolerant Z direction. In this case, we're going to use this to exclude all the upward facing surfaces in our foundations. As well as this, I'm going to be using spring nodes in order to get the polysurface out of the topography mesh. There are various ways to do this without custom packages. I just find this is a good little shortcut. I'll be using Revit 2020.2.2 and Dynamo 2.3.0 for those following along. Without further ado, let's jump in. So I've set up a very basic sample model. Essentially what it has at the moment is it has some building pads. So I have a pad that sort of represents the, I guess the strip footings or the trenches that might be cut into a site. So I've just used a pad at a certain height, and I've used a couple of internalized pads at a slightly higher height to represent where those trenches would stop in the site. Now this isn't necessarily always the way you might model upon a site using, say, structure. You might even just be able to use like the beams and the strip footings and the slab as your intersection geometry instead. So I'm going to be collecting my pads and dealing with them in a very specific way. You might have different methods. Likewise, maybe you might not be excavating trenches. You might just be doing a level excavation and building a waffle slab on top of that. So it all comes down to your construction methodology. I've just got a very basic demo in this case. And I have two topographies. So I started with one topo, an existing phase. In this case, I don't believe I can see it, but I do have two topographies in this case, I believe. No, I don't. So what I need, I have one that's on existing being demolished at existing. That should be demolished at new construction. And then I have a copy of it on the new construction phase. So I have a topography being cut, in this case, by the pads. And then if I go back to my show complete existing phase, I have a copy of the topography that is not being influenced by the pads because the pads are on the new construction phase. And I do need these two elements in order to form a comparison between the before and the after of the topo surface. Now there is a tool under massing and site called graded region, which in this case you can use to essentially compare the cut and fill between two different topographies. I find I get very inconsistent results with this tool, and it's also a very confusing tool to set up, I find, on average. It's not a very clear handheld process, and I find a lot of users really struggle to follow it. So this might be an easier workflow for you, if you know Dynamo. So let's just start off with Dynamo. We're going to need to collect a few things. So the first thing I need to do is collect all of my building pads. So in this case, I'm just going to get a categories drop down, and I'm going to go down to site, and the pad category actually falls under site-pads. I'm going to get all elements of categories, so I'm going to get all my building pads. And in this case, I'm in the new construction phase at the moment, so I should retrieve my 3 building pads. Now I also need to obtain my existing topography. So I'm going to get a select model element node. And I'm going to need to go and pick that original topography, so I can get the one that's not influenced by the building pad. So I need to select this one here. And now I should have access. I believe I probably still need to select it. There we go. So now I have the existing pad, the existing topography and the new pads. I'm going to use my Surface Clamp Z node from my custom package, and I'll just quickly show you what's actually happening inside that node. I don't believe I wrote this one in Python. So in this case, I'm going to use the default values, which is looking for any values of Z between 0.5 and 1. So anything that's facing slightly upwards will be filtered out in this case. So I'm isolating, actually will be isolated. So I'm getting all the surfaces that point roughly upwards. Inside the custom node itself, I'm using mostly code blocks. So I'm taking all the normals at the center of each face of the geometry that I'm obtaining. And in this case, I'm actually just using, I forgot a step here, but I'm essentially just checking the Z value of the vector and seeing if it falls within a threshold. But I actually do need to get the geometry of these elements. I forgot to do that. So I'm going to get element geometry. And because they're pads, I know that the resultant geometry should be solids. So I'm going to get 3 solids. I could use the element.solids node as well, if I know I'm going to get different elements. And in this case, I'm going to use the geometry explode node, just to turn these into their respective surfaces. And this should just leave me with all those surfaces, as they belong to all the surfaces. I'm going to flatten this output because the list structure is quite awkward at this point. And I'm just going to turn off the preview for these 2 nodes. And I should be left with just a single list of surfaces. And I'm going to feed this in to my surface clamp Z node. And what I should expect to get out of this is only the surfaces that are pointing upwards or roughly upwards. See, now I just get those three surfaces. So this gives me some geometry that I can extrude upwards. So in this case, I'm actually going to thicken those surfaces, and I'm just going to thicken them upwards so I can intersect them with the site topography. So in this case, I'm going to get the surface thicken node, and I'm just going to get the thicken both sides node. I'm going to take those surfaces and I'm going to thicken them by just, I'll do 5 meters, just so they're above the topography. And I'm not going to do it on both sides. I'm only going to do it in the upward direction. And now you can see that I'm extruding that pad volume upwards. So now I've created a volume that I can intersect with my topography in this case. I'm just going to union this together using a solid by union. And this should collect them all together. I might just have to look for union. That's the one. And this should give us just one object that we can use to intersect. And assuming they're all connected, I'll just have one solid. Okay, so what we need to do now is obtain the toposurface geometry as well. So in this case, I'm going to obtain element geometry. And you might get some warnings depending on your toposurface. But in this case, I do get a warning about branching polycurves, but I believe I should still get the underlying mesh for the object anyway. Sometimes you'll get the warning, sometimes you won't. What I'm going to do now is I'm going to get that mesh to polysurface node from Springs package. And this will allow me to take my topography mesh and convert this into a valid polysurface that can be used for intersection with solids. And at this point, I'm going to use the geometry split node. And this is pretty much the key to the whole workflow. So I'm going to take my site geometry and split it using my polysurface. And what I should get at this point is 2 pieces. So I'll hide my union. And I'll just create a list flatten function just to put these into a flattened list. And I'm just going to call on one of the indices because we should have 2 objects. We split it in 2 pieces. I'm just going to get an integer slider. And I'm just going to make it between 0 and 1, so I can call on the index at 1 or 0. And we're just going to use this to visualize what the 2 pieces represent. So I'm going to make that my list flatten, and then I'm just going to use a get item at index node, and from that list I'm going to retrieve currently the object at index 1, but I can also get the one at index 0 and sort of see what those two results yield. So I can see in this case I get just the very bottom of the surface plus the solid, or in this case I get the solid fill as it intersects with the site topo surface. In this case my topo surface is fairly flat, but otherwise you should expect to get a pretty accurate representation of your site. We could try raising the site quite extremely to see if we can sort of manipulate those results. So I might make that 5,000, I'll make that maybe 3,000. And that should hopefully give us a more extreme result between the 2 intersections. In this case, we're probably going to have to clean some of this up. So in this case, I actually forgot one step. So at the moment, I made the topography a little bit more complex just to get a better sort of intersection to really see what the geometry would look like. One thing I forgot that is if the element geometry node for the topo surface doesn't fail with a branching polycurve, it actually returns all the polycurves first, and then the last object in that list is the mesh. So in this case, I actually need to introduce a last item node. to make sure I always get the last item in that list. And this should always retrieve the mesh, which will mean that I always successfully collect that mesh, split the site, and now I can obtain those two respective pieces of the site as they're intersected. So now I can see I can get the non-intersected and the intersected volume. And now I can see I have a much more accurate and detailed excavation of the site, including those pad volumes underneath as well. You can see that they're being cut out as well. And as you can probably expect with this, all I really need to do now is assess the volume of this object. So I can get a solid volume. In this case, I'll probably need to retrieve the solid volume node. Now at the moment, this will be in Dynamo native units, so I do need to convert this. So Dynamo native units for me are in millimeters or unitless. We need to convert volume, so we're going to go from cubic millimeters to cubic meters. And we can just get a watch node at this point. And we can see that we're successfully detecting the amount of cut volume that would be required out of the site. So it's a much more easy and straightforward workflow, I think, than trying to get the graded region tool to work. And as well as this, it's a really easy tool to just take from project to project. And rather than introduce the complexity of graded regions into the way your model's set up, you can just run a quick Dynamo study to retrieve the actual number that is being excavated from the site. So hopefully this helps you better assess the cut excavation upon a site in a basic study or even a more complex study. And I hope it helped you specifically, Ruben. So thanks for watching. Hopefully that helped you better find the new workflow, especially if you're a civil or a site engineer trying to make Revit and Dynamo work for you. Good luck. I know it's not easy. So thanks for watching today. If you're not already following and subscribing, feel free to do so. And I look forward to seeing you in future videos. Thanks. Take care. Bye.